All right. So let's kind of get to the heart of this. Suppose y is this function right here. Y is equal to x squared minus x. Okay? And then we've got this function right here. A of x is equal to x to the 5th power plus y x to the 7th plus hx cubed. Okay? If I went through to differentiate this term-wise, let's see what happens. Okay? When I take the derivative of the first term, I get 5x to the 4th. Everyone agree? Okay. When I take the derivative of the last term, I'm taking the derivative of hx cubed. What happens to that h? It's a constant, right? And what happens with constants when you take the derivative? Everybody, they just come along for the ride. What happens when you take derivatives of constants? They come along for the ride. Okay? So what is the derivative of hx cubed? It's 3h x squared. Folks, are there any questions on that? Now, here's the mistake that people make. When I go to take the derivative of this, oops, excuse me, that should be yx to the 7th. Sorry about that. When I go to take the derivative of that middle term there, yx to the 7th, it is not 7yx to the 6th. This is extremely important. And I'm sorry I've got those typos in there. When I go to take the derivative of yx to the 7th, it is not 7yx to the 6th. Curtis, why not? What do you mean? I think I agree.
Because you have to do a rule.
Yeah, I think you're onto it. What factor you use? What information in the beginning of this problem are you using? Okay, so here's the thing, folks. What was h in this? What was h in this function here? Constant. We just inferred that by its placement, by the letter choice we use. But what is y? Is y a constant? Y itself is another function of x, right? And so because y is also a function of x, I cannot treat it as a constant that just comes along for the ride. Okay? So instead, how would we take the derivative of yx to the 7th? Okay? Well, one way to do so is to do the substitution, because we know what y is, so let's actually do the substitution. That would be x squared minus x times x to the 7th. Right? And then as Curtis said, what type of rule are we going to have to do when we take the derivative of this expression? We're going to have to do a product rule on it. So when we go to take its derivative, here's the first times the derivative of the second plus the second times the derivative of the first. Okay. Which gives us x squared minus x times 7x to the 6th plus x to the 7th times 2x minus 1. Okay. Specifically, folks, there is the 7y to the 6th. There's the 7. This expression right here is the y, x to the 6th. That maybe somebody might accidentally think was the derivative of this, but they're missing this whole second piece of the product rule. Okay? All right, so I think we brought that home. All right. In the last example, we saw that, okay, if y is some function, then you cannot just bring the y along as a constant. Okay? And in this case, we were able to figure it out because we knew what y was. At the very beginning of this problem, I said, hey, y is this function right here. So then when we had to take the derivative of a term involving y, we just did a substitution step. But we may not be able to determine what y is. For reasons that I mentioned before, we might not be able to solve for y. But we can still do this derivative just as we did. So let's go ahead and do it again. So without knowing what y is, let's take the derivative of yx to the 7th. Without knowing what y is, the only thing we know is that it defines a function of x. Let's go ahead and take its derivative. Okay? So here we go. Here's the first times the derivative of the second plus the second times the derivative of the first. which cleans up to be 7x to the 6th times y plus x to the 7th times dy dx. And we've taken the derivative as far as we can without knowing what function y is. So this technique right here, this technique is called implicit differentiation. This idea right here is implicit differentiation.